Genevieve speaking. In this presentation, we're building a bivariate empirical discrete probability distribution. We're looking at daily sales of cars at Dicarlo Motors over 300 days. It includes sales at its Geneva dealership, which we call X, and sales at its Saratoga dealership, which we call Y. This is table 5.7 from our text. It shows the number of cars sold at the Geneva and Saratoga dealerships over 300 days. For example, so the entry 33 in cell E5 indicates that for 33 days out of 300 total, the Geneva dealerships sells one car, or sold one car, and the Saratoga dealership sold two cars. So the term we used before was cross tabulation. So this is a cross tabulation of cars sold in the Geneva dealership and cars sold in the Saratoga dealership over the 300 days. From table 5.7, we want to construct table 5.8, the bivariate probability distribution. We called it before in chapter 4 joint probability table. In chapter 2, specifically in chapter 2.3 presentation, we called it cross tabulation of relative frequencies. So in each one of those cells in our table, we want the proportion of the total 300 days period instead of the numbers of days out of the 300. So in cell E15, we want to know what proportion of the whole period 33 days out of 300 represents. So cursor in E15, I get my 33 value, divide that by 300, and I'm going to get that proportion, which is 0.11. This is table 5.8 when we completed it. When we've computed all the relative frequencies or fraction of the whole, so the sum of all of them should be 1, and it is. Each cell in the body of the table gives us a joint or bivariate probability for car sales at both dealerships. The joint probability of selling 0 cars at the Geneva dealership and 1 car at the Saratoga dealership on a typical day is 0.10. So the F01 is 0.10. So each cell in the body of the table gives us a joint or bivariate probability for car sales at both dealerships. And the margin probability are going to be found at the margins of the table. We got the numbers at the bottom margin by adding the joint probability for each column across rows. So each column I added across row. Here we go. By doing so, we get the relative frequency distribution for y. Over here, if y is equal to 0, then the probability of selling 0 cars at the Saratoga dealership on a typical day is 0.18. The probability of selling 3 cars at the Saratoga dealership on a typical day is 0.14. To get the right margin numbers or probabilities or proportion, we did add the joint probability for each row across columns. And so we get the relative frequency distribution for variable x, the sales at the Geneva dealership. The probability of selling 0 cars at the Geneva dealership on a typical day is 0.29. The probability of selling 3 cars at the Geneva dealership on a typical day is 0.09. Because we have a variable x relative frequency distribution, we can easily compute the expected value and the variance for x. The expected value of a discrete random variable x is a weighted average of the values of the random variable, where the weights are the probability of occurrence of each value. So in other words, it is the sum of the product of each value x and corresponding probability or likelihood of occurrence fx. So we're going to simply use the sum of product function in Excel. So x values and corresponding f of x values. The variance of a discrete random variable x is a weighted average of the squared deviations of the random variable from its mean, where the weights are the probability of occurrence of each value x. So in other words, it is the sum of the products of the squared deviation from the mean and corresponding probability or likelihood of occurrence f of x. So here again, we're going to be able to use that sum product function in Excel. So before we can do that, we need to compute the squared deviations. Okay, so, oops, I want to compute the squared deviation over here first. So, getting my x value, subtracting the mean from it, I'm going to put $sign over here because I'm going to want that cell reference to stay the same when I copy that formula down below. Square that and copy down below. Now I'm ready to use that sum product function. So oops, starting over here and the f of x. We do the same thing for our variable y. Now we define a new variable s as the sum of x and y. So it's s is the total car sales for Dicarlo Motors at both dealerships. Expected value of s can easily be computed because it's the sum, because S is the sum of X and Y, its expected value is also going to be the sum of the expected value of X and the expected value of Y. So sum expected value of X and expected value of Y. Because S is the sum of X and Y, the variance of S can be computed as the sum of the variance of X plus variance of Y plus 2 times covariance of X and Y. The covariance of discrete random variables X and Y is a weighted average of the products so of the deviation of random variable X from its mean, deviation times deviation of random variable Y from its mean, so times the weight. So the weights are the probability of joint occurrence of value xi and yj, or joint probabilities. So not as straightforward to compute as the expected value of S was. So for each X and Y combination, IJ combination, corresponding deviation of X from its mean, a deviation of Y from its mean, and a corresponding joint probability of X and Y. So for each X and Y combination, we take the product of those 3 factors, 1, 2, 3, and then add them, all those products together over all the X and Y combinations. So let's get started. So first value of X, all right, is over here. So minus is expected value to get the deviations. So times first value of Y over here minus its expected value to get the deviation, and then times the likelihood of occurrence of that combination XY values. Okay, so moving on, so we're still going with the same value of X, 0, subtracting its mean times the deviation of new value of Y now, because we want a new combination XY value, minus is expected value of Y to get that deviation from the mean, and times the likelihood of occurrence of that XY combination. And moving on, keeping our X value over here, forgot my parentheses to get my deviation from the mean times new value of Y, deviation of that value of Y from its mean, times the frequency of that, or joint probability of that XY combination. When for value of X equals 0, I've gone through all the possible value of Y that can go with that. I'm ready to move on to the next row, or next value of X and different combination associated with that. So deviation of X from its mean value, first value of y that can go with that is 0. Take the deviation of that from its mean, multiply by the likelihood of occurrence of that x equal 1 and y equal 0 combination. Okay, last product. And here I have my covariance. Once I have my covariance, the variance of x is easy to compute. Looking at variance of y plus x, plus variance of y plus 2 times covariance. Here we go. Rounded to 4 decimal places, the variance for S is 2.3895. Alternatively, to compute expected value of S and variance of S, we could have built, or first built, table 5.9 by extracting from table 5.8 the values for S and corresponding probability of likelihood of occurrence for each value of S. So f of S, that's the likelihood of occurrence of each value of S. So x value range from 0 to 3 and y values range from 0 to 5. So if S is defined as x plus y, then our S values are going to range from 0 to 8. Our probability f of S correspond to our joint probabilities from table 5.8. So for S value equals 0, that can occur only when x equals 0 and y equals 0. So that f of S over here correspond to f 0, 0 over here. S equal 1. That can occur when x equals 0 and y equal 1. Okay. Or x equal 1 and y equal 1. So f of S is the sum of those two joint probabilities. Okay. 2, S equal 2, that can occur if, so y equal 2 and x equals 0, or both x and y equal 1, or x equal 2 and y equals 0. So that's the sum of those three, and so on. Once we figure out all the probabilities for all our S value, we can make sure that we didn't make any mistake by summing them all, and we should find it's equal to 1. So we are ready to compute the expected value and the variance of S. So expected value is a sum product, the sum of the product of the values and corresponding probability. Okay, now we can compute the square deviations, $, so that this cell reference doesn't change when I copied. So square, oops, my parenthesis is wrong over here. Copy that, ready to compute my variance. Oops, It's the product of square deviation and its corresponding probability of occurrence. Rounded to the 4 decimal places, it's easier to see that we got the same expected value and variance value for S as we did before. And this concludes our presentation about bivariate empirical discrete probability distributions.